a quick rundown on what you need to know about the physics of musical instruments. You may wonder how it's possible to get such a nice tone out of this pen. So this is it. Well, first you've got to understand what a standing wave is. So a standing wave is also called a stationary wave. It's a wave that oscillates in time but does not move in space. So what does that mean? What does that look like? PHET simulations. So here we have a wave generator. It's sending a pulse down towards this fixed end here. And you can see how that pulse gets inverted. And then there's a new pulse that was produced. They're going to meet up, and as you know, they're going to interfere. These ones are going to cancel each other out momentarily. So let's see what that looks like. Gone right there, and then they pass through each other and then continue on their way. What if we just continued sending pulses forever, kind of like this? So instead of sending just one pulse, we send a continuous wave. If the frequency is just right, then the reflected wave will match up with the incoming wave and interfere constructively in one spot and always destructively in one spot. Those are those green points called nodes that are not moving very much. They shouldn't be moving at all. And then the points of maximum wave action are antinodes. And you can also see lambda from there. So that all depends on the length of the string or the length of the air column that you're dealing with. So again, some key terms are the nodes. The nodes are the points on the standing wave. Right here you can see that don't move. And then we have antinodes, are the places where the wave moves at a maximum. This is a standing wave that is fixed at both ends and has 4 nodes in it and 3 antinodes. You could have any number of nodes or antinodes depending on your situation. Which brings us to the types of musical instruments that we have. They can be modeled in 3 different ways. Either they're fixed at both ends. An example would be like a guitar string. Or they're opened at one end and fixed at the other end, kind of like that pen tube I have in some pipe organs. Or they could be open at both ends, like I think a recorder and a flute might be modeled that way. So let's explore this first case first, where you have a double fixed end. This looks like a lot of information all at once, but let's take a look at what we have here. So this is like a guitar string which is firmly fixed in 2 places, at the neck and at the bridge. And this is its fundamental mode of vibration. The string can vibrate up and down this way. Now we say there's a half a wave here because we only have one crest or one trough, depending on how you look at it. It's easier to see the full wave in this next diagram here. So if this is one wave, then the first diagram must be a half a wave. So we call that the fundamental. We also call it the first harmonic. And then you can see every time we go up a harmonic, we just add a node in the middle and a half a wavelength as a result. So from the second harmonic to the third, we have 1, 2, 3, 4 nodes and 1.5 wavelengths, and this is the next harmonic, which has 1 more node, half extra wavelengths. What does this mean? This means we can answer questions like this. So this example is a guitar string is 68 centimeters long, and a wave propagates along the string at 147 meters per second. So what frequency does this string make? Well, the thing is, when a guitar string vibrates, it'll vibrate at all of these at the same time, so you get a nice rich tone. But this question is asking, what frequency does the string make when plucked and vibrating at its fundamental resonant frequency? So let's attempt this problem here. What do we need to know? The fundamental frequency is this one here. We know that there's a half lambda right here. If the length is 68 centimeters, that means the length is equal to a half lambda. So the wavelength is just equal to twice of 168. So that's 136 centimeters. Now, from the universal wave equation, V equals F lambda, given that the velocity is 147, and lambda is 1.36 meters. Careful, I just changed to meters just like that. You can figure out the frequency of this note is 108 hertz, which happens to be A2, if that's interesting to you. And if you're curious what that sounds like, here it is. Okay, let's tackle the next case. This is the next type of vibration here, where you have one open end and one fixed end. Very similar, but where you have a fixed end, you still have a node, but at the end it's open, so you get an antinode. How many waves fit in here? It's a quarter wavelength. It's hard to see, I guess, exactly until you see a full wavelength right there. And then an extra quarter, that would be a half, right? So this is 1 1/4 wavelengths, this is 3/4 wavelengths, this is a quarter wavelength. This is the fundamental, first overtone, second overtone, etc. And these are the harmonics. Notice they don't go 1, 2, 3, 4. For this type of vibration, it skips and only does the odd harmonics. If that's curious to you, well, maybe you can ask about that in class. So we did a question similar to this one, and let's just try it again. Okay, so what frequency will a 10 centimeter pen tube vibrate at most strongly when you blow across the top of it? So when it says most strongly, we're talking about the fundamental frequency there. So this is the 10 centimeter long pen tube vibrating at the fundamental frequency. It's holding a quarter wavelength. Quarter wavelength is 10 centimeters, which means that lambda is 40 centimeters. So we go back here, V is equal to F lambda, and if we knew the speed of sound in air, we could figure out the frequency of vibration. It depends on the temperature, but a good number to use for room temperature is about 340 meters per second. With those numbers in, we can calculate the frequency of this pen tube to be 850 hertz. Of course, that number could change if the temperature of the air is different on that day. And here's that sound again. Okay, and here's the final case. What about if your resonating chamber is open at both ends, like an empty pipe? You can see the standing wave formations here. This is the fundamental. Antinode, node, antinode. And then if we add a node in here, so we have two nodes, we get the second harmonic or the first overtone, and so on. Notice how many waveforms there are in the fundamental here, a half, then you add a half each time. So very similar to the previous ones. Let's just try this example here. It says calculate the frequencies of the fundamental, second and third harmonics for a 1 meter long pipe, hollow at both ends. So we'll model that like this. Here is the fundamental. This is a half wavelength. Since the length of this is 1 meter, we can say that 1 is equal to a half lambda, so lambda is equal to 2 meters. That's at the fundamental. What about at the second harmonic? Second harmonic, we know to add in a node. How do you do that? That's hard to draw sometimes, so I just put like a loop in the middle and then draw it like this. And that I've done the job there. And we're going to need the third as well, so that means I need to add 2 loops. 1, 2, and then my ends are like this. But I know this is equal to a full lambda. A little bit hard to notice, but check it out here, right? This is 1/2, and then there's a quarter, and then there's the other quarter, right? What about this one? This is a full plus a quarter and another quarter, so that's 1.5 lambda right there. So 3/2 lambda. So the length is still 1, but to find the second resonant frequency, the wavelength will be 1 meter. And then similarly, for the third one, we have 1 meter is equal to 3 over 2 lambda, which makes lambda 3 equal to 2 over 3 meters, or 67 centimeters if you prefer. Okay, so now we just need to calculate the frequency based on the speed of sound. We'll choose the same speed of sound, 340. The frequency multiplied by 2 here. So in the first case, the frequency is 170 hertz. That's the fundamental, which I'll denote with F1. The other case is 340 equals F times 1. That's easy. Frequency is equal to 340 hertz. Notice it's an integer multiple, just times 2 of the fundamental. And we can use that same reasoning to take this and multiply it by 3 to go from here to here if we want to. That's a pretty good trick. So 170 times 3. We should get a final answer of 510 hertz. But from the beginning, 340 equals F times the 2/3 of meter that we have here. And just checking on my calculator, we do get 510 hertz. Let's clean this up a little bit. Let's put our formulas in everywhere. And so there's a summary of that pipe organ that we're calculating for, vibrating at 170, 340 at the second harmonic, and 510 at the third harmonic. Well, that's everything you need to know for calculations for musical instruments.